So let's start from the relatively lower specific speed regimes. And the first case that we are going to look at is secondary flow in radial impellers. And you can find detailed information on this from this paper, which was published in the Journal of Turbomachinery. Now, essentially, what you see here is a conventionally designed pump impeller. And actually, the specific speed of this impeller is about 280, using head in meters, RPM, and flow rate in meter cube per minute. And what you see here is the CFD prediction of this conventional design, very close to the suction surface. And what we actually notice is quite strong secondary flows. So what you see in this middle figure is actually we are looking inside the boundary layer, and these flows seem to be carrying this low momentum fluid on the suction surface and dumping it onto the shroud suction surface corner. And in fact, if you look at the exit flow from the impeller, you can see the accumulation of this low momentum fluid at the exit plane, right here. And what this means is you actually get a high velocity region at the hub pressure surface corner here. And this flow non-uniformity at the exit of the impeller is often known as the jet wake flow. And this has a major adverse effect on the performance of the pump stage. So first of all, you get very high stage losses because of the mixing losses. You also get fairly poor performance of the downstream diffuser. And also this source of non-uniformity can be a major source of pump instability, or the sort of hysteresis that you see in pump characteristics, and so the stall performance. So in fact, you can see here in the conventional impeller that these gradients of reduced static pressure here on the suction surface correlate quite well with the secondary flows right here. And if we can somehow try and reduce these gradients of reduced static pressure, then we should be able to reduce these secondary flows. And then we can eliminate this non-uniformity, which is very important for the impeller and stage performance in pump applications. So the question then is, does your pump suffer from secondary flows? And if so, what can you do to suppress them? So what we have done here is that we have plotted Cp, that is the reduced static pressure coefficient, on the hub and shroud on the same plot. And this in fact closely relates to the blade surface velocity. And so you can actually directly generate these plots in your respective CFD software. And essentially what's driving the secondary flow here is this delta Cp. So the difference between the Cp on the suction surface of the hub and the suction surface of the shroud is what's creating these gradients of reduced static pressure, and hence generating these secondary flows here. So what we then want to do is to try and close this gap as much as possible. But we really want to do it in a way that ensures we still get the same head from the impeller. So we don't want to reduce the head from the impeller. We still want the same overall head, but what we want to achieve is a reduction in this gap here. And in fact, in inverse design, what we control is the blade loading, which directly relates to the pressure jump across the blade at the hub or shroud. And then by using an appropriate choice of blade loading, what you can see they have done here is that by reducing the gap in this aft part of the shroud here and increasing it in the fore part, and the opposite, that is increasing it in the aft part of the hub here and then reducing it in the fore part, we actually then close this gap that is driving the secondary flow. And as we can see, that the gap is reduced, and as a result, we can actually reduce the secondary flows in the impeller. So now if you think about looking at the blade loading, which is the difference between the pressure distributions of the suction and pressure surfaces on each streamline, we find that this type of loading, in fact, can help you to reduce secondary flows. So what you see here is the green line is the shroud, the red line is the hub, and essentially by using a forward-loaded distribution at the shroud and an aft-loaded distribution at the hub, but you're actually reducing the surface velocities on the shroud suction surface, and you're increasing them on the hub's suction surface. And by doing a combination of these two, that is a forward-loaded distribution at the shroud, aft-loaded distribution at the hub, we should be able to get a net reduction in this reduced static pressure gradients on the suction surface, which is what we are actually trying to achieve here. So then you can see this effect better in this image. So this is actually an impeller that was designed keeping exactly the same meridional shape and exactly the same head as the baseline impeller. But by using that set of blade loadings, we could actually reduce these gradients. And then by reducing these gradients, we can see here we could actually eliminate the secondary flows on the suction surface. And as a result, we get a much more uniform exit flow from the impeller.